Hello everyone, I'm Shahriar Tanvir. My group mate is SM Tasmi Hassan. For the past 3 months, we have been working on a project called Design and Analysis of Floating Hybrid Solar Wind Plant for Residential Area. We'll go through the introduction, the objective of the project, the design of the project, the simulation result that we have found from running our design in Simulink, the reliability parameter and design specification of those system, and discuss about the project and put some remarks on the project in the final conclusion. The primary focus of this project is to leverage renewable energy sources to create a sustainable and efficient power generation system by combining solar and wind energy. We aim to utilize the strength and both technologies. This project employs MATLAB Simulink for system modeling and simulation, aiming to design and analyze a floating hybrid solar-wind power plant on a lake, which is situated in Bangladesh, Kaptai Rangamati. Our primary goal is to choose the best solar model and conduct a reliability analysis for the design. We have choose three solar model and a regular wind power model. Additionally, we discussed the financial and environmental feasibility of this hybrid system using Homer software. And the objective of this project is design and model by creating a floating hybrid solar wind plant model and determine the most efficient solar PV model, and then simulate an analysis about the project to generate voltage output graphs for various solar PV and wind turbine model using MATLAB Simulink, and identify design specification and reliability parameters of the floating hybrid project, and finally economical viability by investigate the cost summary and perform an economic analysis of the hybrid model to evaluate its financial viability and environmental impact. To discuss the design of the project, here's the Simulink model design of solar PV. The solar PV system is designed to absorb sunlight and convert it into DC electricity. This involves selecting the most efficient PV models and configuring them for optimal performance. And here's the Simulink design of wind turbine. The wind turbine system starts with wind speed as the primary input. The aerodynamically designed blades capture the kinetic energy, converting it into mechanical energy, which is then transformed into electrical energy. Both systems are integrated through a busbar and buck boost converter to manage and stabilize voltage level effectively. Here you can see the schematic design in Homer software. We have connected the wind power plant with the capacity is 3 kilowatt. I have connected into AC busbar and converting into DC, and the PV solar panel connected with the DC busbar and converting into AC. So the whole project is based on a residential area where the peak energy would be 1.86 kilowatt, and it will provide 10,000 kilowatt hour per day. We have implemented a battery in the system. Let's talk about the result of the sim Let's talk about the simulation result of solar PV. This graph shows the irradiance versus voltage output of different solar PV models annually. Here you can see the sun power demonstrate the highest voltage output for the same irradiance data used across three models, which are Sun Power model, Kyocera Solar, and Canadian Solar. The seasonal variation in irradiance peaked in March at 6,480 watt per meter square and reached their lowest in July at 4,300 watt per meter Each solar, each solar PV model responded differently to these changes, with distinct voltage peaks occurring at different times of the year. Here you can see the SunPower solar panel achieved the highest voltage of 56.95 volt in July, making it the most efficient model in our study. Kyocera Solar reaches at maximum voltage of 38.62 volt in July, and the Canadian Solar records a peak voltage of 37.85 in July. These models have been enhanced efficiently at converting lower amounts of sunlight due to temperature effect. Solar panels typically operate more efficiently at cooler temperature, which can occur during the summer mornings or evenings when the irradiance is lower. Now let's talk about the wind result. The graph illustrates the voltage output from our wind turbine system. Here we can see the voltage drops significantly as wind speed decreases from 8 meter per second to 7 meter per second, then peaks at 5 meter per second, indicating optimal performance. The system shows a clear peak at 5 meter per second, suggesting this as the optimum wind speed for maximum voltage output. Voltage output decreases consistently at lower wind speeds, highlighting the importance of optimal wind speed for efficient energy. Now the rest of the part will be discussed by my groupmate SM Tasmi Hassan.
Thank you, Shahriar, for giving me the floor. This is SM Tasmia Hassan. So I will be discussing everything related to Homer result and as well as the reliability analysis, the design specification, and we are going to wrap up the presentation with final discussion and conclusion. So let's move to the simulation result that we obtained from Homer. So this is the cost summary of the simulation result obtained from Homer, where we can see that the wind turbine actually is the highest. It is the most costliest part of the project, which is around 280,000 USD, and the levelized cost of energy is 7.94 USD per kilowatt hour. That is, so we can say actually that this price is very high for consumers. If for electricity bill it is actually a bit higher, and but in the discussion and conclusion part, we are going to definitely see that how government policies can help reduce this cost. So there are many costs involved and many policies involved that actually that government can help to make sure that the consumers as well as stakeholders, whoever want to invest in any sort of renewable project, they will be benefited. So in this way we can definitely see that the cost will definitely get lower. And then moving on to the next result, uh, this is the electrical part of the project that we also obtained from Homer. We can see that the excess electricity is 1.88%. Like after like supplying it to the residential area, 1.88% is the excess electricity, and which is 60 kilowatt per year. And as we used SunPower to actually simulate the Homer, so we can see that SunPower is giving out 523 kilowatt per year. So this excess electricity, which is the 60 kilowatt per year, this actually is transferred to the national grid or stored in the battery for later use. And we can see that renewable fraction is 100%. That is here, this project is completely environmentally friendly, we can say. And we can see that the peak electricity level is high in the month of June and July, which actually coincides with, which actually is similar to the result we can with that Shahriar have explained from the Simulink result. Also we saw that the peak electricity is around July. So this is the electrical part. And then this is the renewable usage. So obviously we mentioned that the renewable part of this experiment is actually it's very rich in renewable. It's the highest in renewable. It does not have any sort of GHG emission or any sort of uh, fossil fuel involved in it. So therefore the renewable percentage is very high, and we can see that the percentage of renewable everywhere is above 100%. So it clearly indicates it's an environmentally feasible project. And then moving on to another part of our objective, which is also the last objective of our project, which is the reliability analysis of this project actually. There, so we can see that the solar PV, if we see the result of reliability graph of the solar PV, we can see that the solar PV's probability is around 0.64, that is, it is 64% reliable. And probability, that is the reliability, is inversely proportional to cumulative distributive function. So when reliability increases, cumulative distribution function decreases, and if reliability decreases, cumulative increases. So we can see that along with solar irradiance, when solar irradiance is like when solar irradiance increases, with increasing solar irradiance we can see that reliability decreases. So therefore with increasing irradiance the cumulative density, the distribution function increases. So they are inversely correlated. So the reliability of our project for the solar part is 64%. You can say that it is 64% reliable. And the highest cumulative probability obtained is 0.78 approximately. So yeah, with irradiance we can say that obviously, and we have also from our Simulink result we have seen that the our actually it's not always necessary that solar PV with every high irradiance it is going to give high voltage output, because voltage output and irradiance is not directly related. So this also matches with our reliability parameters, that with high irradiance does not necessarily means that the solar PV is reliable. With low irradiance it is showing a high reliability, which is 0.64. So this is one important thing to be noted, that with for the solar PV sun power that we used, with irradiance of around 4500 we get 0.64 reliability, which also exactly we found that in the Simulink result also, the with low irradiance the solar PV works efficiently. Okay, then moving on to the next graph. This is just a normal distribution result, that in between 4 to 6 the probability density is the highest. This is a normal distribution graph. And then moving, so let's talk about the reliability analysis of the wind turbine. So similar like solar PV, the wind turbine also, with increase in speed the reliability decreases, as we can see from the last graph. And reliability is inversely proportional to cumulative probability. So when reliability is decreasing, we can see that the probability increasing. So also in wind, we can say that high speed does not necessarily mean that it will be highly reliable at high speed. No, it's not the case. In fact, the lower the speed, the more the wind is efficient, and the wind turbine is more efficient. So yeah, this is the reliability analysis of our wind turbine. And now let's move on to our design specification. So to design a hybrid, floating hybrid solar wind plant, we need around 86,125 meter square space for the solar to make and 80 meters square for the wind turbine to be implemented. In total, we need actually 86,205 meters square, and this will generate 122,506 megawatt hour in a year. So, and the rating of that floating hybrid power plant is around, its total power output is 13,97189 megawatt. That is around, you can say that it's 13.97189 megawatt. That's the power output. So to generate this power output, 13.97189 megawatt, we need that to build the floating hybrid power plant around 86,205 meters square. So these are the design specifications, and let's move to the reliability parameters. So we can see that our wind turbines mean time to failure is around 4.431 years, and mean time between failure is 5 years, and mean time to repair, it takes half a year to repair approximately the wind turbine, and the availability is 88%, which is good. And the design lifetime is 25 years, which is more. So the solar reliability parameters of solar is, we can see that it's less compared to wind in terms of mean time to failure, design lifetime, mean time between failure. So in everything, the solar PV is less compared to wind. So let's move on to discussion. So sun power is definitely better compared to other models, and it's giving the best output in July. And the reason is because it works at a lower temperature better compared to higher temperature, whereas the wind is giving best output in 5 meter per second due to its design. And also in reliability analysis, we have seen that in higher speed the reliability of wind decreases, whereas we need some government policies that must be considered whenever implementing any high cost renewable project, like policies like subsidies and incentives, feed-in tariffs, regulatory support, investment in research. These things helps actually making it economically feasible. To wrap up the discussion, we have already seen that solar have lower reliability compared to wind turbine, and we end up this presentation with the conclusion that sun power is the best compared to other models. Government policies must be brought into limelight to make the project economically feasible. However, certain things like reliability analysis, performance, stability, cost effectiveness, environmental impact are most important when considering such a renewable project. And if these things are considered, then by considering this aspect, better hybrid floating solar plant can be implemented in lake, and that can be also economically and environmentally feasible as well. So this is the things that actually can make it economically, environmentally feasible. Reliability analysis can be also done to make it more reliable, as well as a proper design. So these things must be brought in together to make the floating hybrid solar power plant a successful power plant, and can be made properly for residential load. Thank you. Any questions?